In recent years, we have seen a rise in object-based media experiences. These are immersive media experiences where the composition of media objects is deferred to end-user devices based on some metadata. So these experiences flex to users' preferences, viewer conditions, consumption patterns, etc., and allows for greater degrees of personalization and provides new forms of entertainment. So as content providers, we are looking into providing universal access for object-based media experiences where any device, a new device or a legacy device, can play back any experience. This is challenging because these experiences can have multiple formats, be designed for multiple devices or users, have multiple viewpoints or multiple streams. So we have built a prototype that demonstrates 3 software approaches that we believe are key to efficiently deliver universal access to OBM experiences. Central to our prototype, we have a write once, run anywhere approach. So this is a sustainable way of targeting multiple platforms where we have one code base which works for all of our target platforms. And this is particularly important in a world where the number of devices which can play back media objects is ever increasing. We're also using a games engine-like runtime approach, which enables us to provide a toolkit of efficient capabilities that can be reused by different experiences and run smoothly on all of our target devices. And we're trying to achieve universal access, so we want to ensure that any client can run any experience. For experiences which require compute-intensive tasks, we offload those heavy tasks to a server in the cloud and remote stream the resulting experience to low-end client devices. So our prototype is a single media player which uses these 3 approaches to play different types of experiences, including those rendered in the cloud. So we have therefore called it the Single Service Player, or SSP. It is based on the interface for BBC iPlayer, and users can navigate through the carousels to select a number of experiences to play. Our demonstrator uses a write once, run anywhere approach. By using a cross-platform build system, our one codebase written in C++ runs on all of our target platforms. So I'll take you through them one by one. Our SSP runs on all major browsers: Chrome, Firefox, Safari, and Edge. We compile our C++ code to WebAssembly to make it run in the browser. This allows us to have near-native performance in the browser. We use Emscripten to bootstrap our generated WebAssembly binaries to the Web API. We compile to native binaries too. Using the same C++ code, we therefore have our application working for macOS, Linux, Raspberry Pi, and we've also built an Android APK from the same code too, so we can run our app on Android devices, phones or tablets, as well as Fire TV. There are a number of advantages using one codebase for all of our target platforms. It allows us to have the same look and feel, and for web specifically, it means that we are not relying on CSS in the browser. We have feature parity, and we can ensure that the behaviour is the same across all of our target platforms. And it's a sustainable way to develop and deploy new features and experiences, as we do not need to rely on different development teams for different target platforms. To play back diverse object media experiences, we have built a cross-platform media runtime on top of which these experiences can run. The runtime utilises a number of shared capabilities that we have implemented in our C++ codebase. These capabilities are cross-platform user inputs, where we use SDL, which is Simple Direct Media Layer, a cross-platform abstraction layer which enables us to have low-level access to mouse, keyboard, touch and gamepad APIs. We have a render interface, where we provide a high-level rendering interface which itself is based on SDL. We have video and audio playback. This is either delegated to the browser for web builds or using our own C++ implementation for native platforms. We have implemented MPEG-Dash support. We have media decoders, audio and video decoder use FFmpeg, and where available, hardware acceleration is also utilised. We have object-based experience logic, which provides the business logic for object-based experiences such as branching narratives, where users can make choices. And we have our remote experience client, which streams content from our cloud rendering server. These core capabilities can be used to build a number of different experiences. Using our set of capabilities, we're able to demonstrate the playback of linear AV programs, and we've also implemented play, pause and seek functionalities. We can also play back interactive experiences. This is an example of an interactive branching narrative, where users can interact with the story and make choices. Interactions can be made with a mouse, keyboard, touchscreen, or remote control, depending on the platform. On Macs, Linux, browsers and Raspberry Pi, users can interact with their mouse or keyboard. On Android platforms, the user can control the experience with touch interactions. And on a Fire Stick, users can use a remote control to make choices.
Right then, hat it is.
Our challenge as a content provider is to offer new experiences that will work on all devices, including legacy devices. But there are some devices that may not have the computational power to render complex experiences. So to achieve our goal of universal access, we have been experimenting with lifting compute-intensive tasks like the rendering of a complex object-based media scene into the cloud and remote streaming the resulting video frames onto end-user devices. So the user inputs are captured on client devices and streamed back to the server, and this allows highly interactive and immersive experiences to run on thin clients without incurring any significant loss in quality of experience. So we have implemented our Remote Experience Streaming Service, or RXS, to demonstrate the feasibility of this approach. Provisioned GPUs are located on AWS instances, and they use NVIDIA's APIs to capture and encode the screen in real time. And we use Opus for the audio. And they are both streamed to the client using SRT sockets. Our experience runtime contains the functionality to trigger rendering of the remote server and to receive and display the stream. So we've implemented our RxS client for all native platforms. The web requires the integration of low latency streaming technologies such as WebRTC, which is on our list of future works. So obviously key to the quality of experience here is the response delay time as well as the frame rate and resolution. So we've taken some initial measurements to the response delay time between user interaction and the screen responding to that interaction. And this shows that we have achieved very reasonable delay times on different client machines for HD content at 50 frames per second. We have tested our RxS system on a Linux machine, and our measurements show that the response delay time on average is around 60 to 90 milliseconds. We have also tested RxS on a MacBook Pro. The average response delay times for these machines are around 90 to 130 milliseconds. We have also implemented touch interactions, so we are able to stream and interact with the experience using an Android phone or tablet. Our round-trip delay time is a little higher, between 210 and 270 milliseconds. But what we think is particularly exciting is being able to interact with the experience on this little Raspberry Pi Zero W, a device that costs less than $25 single core with 512 megabits of RAM, a perfect example of a very low embedded device. On this device, our round-trip time is slightly higher, around 300 milliseconds. It is worth mentioning that on a local server, the response delay time was around 25 milliseconds, which means that a proportion of the delay we've measured in our client devices is actually due to the experience itself. So, as we expect to use this technology to make immersive and interactive experiences accessible on all devices, we consider that these delay times are acceptable and would allow users to interact with the experience with a reasonable to good quality of experience. To conclude, Our demonstrator shows the validity of our software approaches to deliver object-based media experiences universally across a diverse range of devices. Our single codebase approach can be used to implement a cross-platform framework which builds and runs for a number of platforms from one maintainable C++ codebase. We have also provided a games engine-like runtime for our media player, which provides a toolkit of capabilities on top of which object-based media experiences can be run. Finally, we have shown that offloading some compute-intensive tasks to the cloud servers and streaming the resulting experience as video is a viable solution to render and distribute complex object-based media experiences to lower-end devices. And we have achieved an acceptable quality of experience. This ensures that no device is left behind and we achieve universal access for our audiences.